Okay, yes, the angle on the magnetic one was 2.1 degrees, not 21 degrees, because I'm really stupid. Okay, so let's talk about the,
It's 2.1 degrees?
Yeah.
oh,
I'll put 21. Mm.
it's two, otherwise, this, no, it couldn't go the way it went, no.
Yeah.
Yeah, the angle is 2.1 degrees, okay? Not, there was the video that showed it, it's really, really shallow.
Yeah. 21's pretty shallow too, though.
No, 21 is like this, okay? Okay. Oh, dear Lord. Okay. All right, so here's the deal. So let's talk about the two parts of the inclined plane, okay? So here's the deal. The first one dealt with static friction. And by the way, I said this yesterday, you keep these labs completely separate when you hand them in. The two labs do not cross each other. They're, no, nothing. They are completely separate. They completely separate. So here's what happened on the first one. So imagine this is your inclined plane, and here's Albert Einstein, okay? So if I take Al and put him on here, right? And I lift him up, eventually Al is going to begin to slide. Now, prior to that, nothing happened. So this is a situation where just because you're applying a force doesn't mean that you're going to have an acceleration. So when I was sitting here, okay, laying there, there was some force parallel that was acting down. So the gravity mafia was trying to drag Al down, okay? But what was happening was the frictional mafia was acting upward. So this is a situation where I would say, okay, hey, here's the force parallel of, so this is what I might ask you on the test, on Monday, by the way. I might say, all right, this thing will not stay up today. So let's say that, hey, there's a force parallel of 2 newtons, okay? And the force friction is 3 newtons, okay? I'd say, okay, you have a block sitting on an inclined plane. The force parallel is 2 newtons. The force friction is 3 newtons. What's the acceleration of the system? And I might say the acceleration might be, 1 meter per second squared, 2 meters per second squared, 3 meters per second squared, or 0 meters per second squared. So if this is a situation, you have a force parallel of 2, a frictional force of 3 newtons, what's going to be the acceleration of the system? Do not make this difficult. 0. It's a goose egg. It's not going to accelerate. You don't have enough force parallel to cause this thing to move. So if the applied force that you were given is less than the frictional force that's holding it, you're not going to make this thing move. Just like, hey, here's a 1 kilogram mass. It weighs 9.8 newtons. If I apply a little bit of upward force to it, okay, I'm kind of straining a little bit, but it's not moving because of the fact that the upward force that I'm applying is less than the gravitational force that's holding it down. So again, just because you're applying a force to a system doesn't mean that you accelerate. Okay? You have to have an imbalanced force. Some force has to be bigger than the other one to make that thing move. Okay. So eventually what happens is this thing began to slide. Okay, so you got Al, right? If I lift this up, Al eventually begins to slide. Eventually begins to slide. There he goes. Okay? When he fell as well, but anyway. So we said, okay, U equals force friction over force normal. And that's going to be, we set that equal, you go through the math, you get tangent theta. So the first thing that you had, the only thing you had to do at the beginning on that static friction was take the tangent of that angle, whatever that one, what was the angle like?
12.
12, okay. That was 12, not 1.2, that was 12 degrees, okay? So literally, all you had to do is take the tangent of 12 degrees, those are your coefficients of static friction. But listen to me. That only works with static friction, okay? that only works with static friction, nothing else, okay? Now, the next thing is they set it at exactly 30 degrees. And what was the values that I sent out? What was the applied force? Like 2.4 newtons, and it weighed 3.0,
3.8.
and the angle was 30 degrees, okay? So, here's the deal. As soon as you know an angle and the weight of the object, what are the two values that you can find right away? You know the weight and you know the angle. So what can you find right away?
Parallel and normal.
Sorry, I forgot I had it off.
It's okay.
Force normal and force parallel.
Yeah. So, go away. So, your force parallel is Fg sine theta, right? Which in that case is going to be 1.90 newtons. So, depending upon how you choose to set up your system, that's either going to be a negative value or it's going to be a positive value. Okay? I don't care how you set up your system. Just, you have to be consistent with it. Okay? Most people define down as being negative. So, here's the deal. So, I've got a negative 1.90 Newton force acting down. So, if this was a perfectly frictionless surface, okay, if this was the magic frictionless block, my applied force going up would be exactly 1.9 newtons. Okay, that's all I would need to apply, is exactly 1.9 newtons. Okay, because that block isn't going to move itself up the inclined plane. So if it was a perfectly frictionless surface, I'd only have to apply 1.9 newtons of force. But I have to apply 2.4 newtons. So what accounts for that additional force? What's that force doing? What's it overcoming?
Friction.
Friction. So if you take 2.4 and subtract 1.9, you get like 0.5 newtons. So my frictional force then, going down the hill, is going to be negative 0.5 newtons. So here's what's important. You're at a constant velocity, so the sum of the forces is going to equal to 0. And I beg of you, if you get on the test, and you're going to have a problem like this, I promise you, you're going to have a problem like this on the test, okay? Come in here and go, okay, force applied, force parallel, force friction, force net, okay? Set up these charts, because here's what I can tell you over the years of these type of problems. The kids that get it right, okay, almost always have this chart. The kids that get it wrong never have the chart. Okay, that's the honest God's truth. I can promise you, every kid that misses this question refuses to draw the chart. And why, I don't know. I don't know if it's a religious thing or what. Okay, it's like, oh, I belong to the church of the anti-chart. Okay, not the anti-Christ, but the anti-chart. Okay, good for you. Weird, but let's go with it. Okay. Anyway, so if you know you're at a constant velocity, and again, every force problem that's going to be on the test, every problem that's going to be on the test, what are the two choices that I have to make on every problem I write on this test for Monday?
Constant velocity or not?
Yeah, I'm either going to make it move at a constant velocity and that net force is going to equal to 0, or I'm going to make you accelerate and that net force does not equal to 0. Those are the only two options that I have on any problem on this test. Okay, that's it. There is nothing else. Okay? Either this adds up to equal to 0 or it doesn't. Okay, that's it. That's it. So start with that idea. And then if it is accelerating, what are my only two options?
Up and down.
Yeah, I can. What is this, kind of a Roman gladiator thing? Live, die, up, down, speed up, slow down.
I was true, so I didn't want to say it like too loud, you know, but like you got the picture, didn't you?
Yeah, I did. I got it. Okay. So I'm just gonna punch you today. So yeah, and if I choose to make you accelerate, I can either make you speed up or I can make you slow down. That's it. Now, if you're speeding up, what do you know about the sign of velocity and acceleration?
They have to be opposite.
They're if they're slowing down, they're going to have
The
opposite signs. If they're speeding up, they're going to have
Same.
the same sign. That's it. Okay? So literally, it's a mathematical thing. Okay? You have a 50-50 shot on any problem to either make it speed up or slow down. And if it's accelerating or it's a constant velocity. Okay? So literally, if you think about it, there's only 3 types of problems I can give you. I can make you speed up, I can make you slow down, or I can make you move at a constant velocity. That's it. That is it. There is nothing else I can do. You are pulling this block up at a constant velocity. This is going to be 0 newtons, okay? I'm not asking you to add up to pi or, the square root of -300. 0, okay? Oh, you knew your applied force. I gave you that number. That was positive 2.4 newtons, if you define up as being positive. That means these 2 negative values here have to add up to 2.4.
What?
What are you doing?
So it helps relax my muscles more. Like I had practice points, so like my muscles are tight,
Okay.
I'm like rolling them out.
Okay, I don't have my glasses on, and I swear to God, I thought you had like a green apple, and you were like polishing the apple while rubbing it on your shoulder. Okay, that's what I'm going. What are you doing to that apple? Okay,
No, I don't
All
like
right.
apples like that.
okay. From up here without my glasses on, that's what it looked like. It was like, what is this kind of fruit therapy or what? Okay. All right. So you calculated the force parallel by taking Fg sine theta. So that's negative 1.90 newtons. My force friction has to be then negative 0.5. Okay, that's it. That's it. Now, when you draw this diagram to scale, right? When you draw this to scale on another sheet of paper with a ruler, and you're going to take a protractor and you're going to draw this at 30 degrees, these are the 5 forces that I want. On any inclined plane problem, there are always a minimum of 3 forces. Gravity, force parallel, normal. Sometimes you're going to have force friction, sometimes you're going to have an applied force. But you're always going to have at least those 3. So when you get done, this is what it should look like. Okay? And again, I want to see the scale. Did you let 1 centimeter equal 1 newton? Did you let 2 centimeters equal 1 newton? What did you do? Okay. Now, when you get to the first problem down below, okay, what are the 2 most important words on that first problem down below?
Force applied.
Nope.
Constant.
Constant velocity.
Oh.
Constant velocity. You're going to make everything add up equal to 0. Again, so on problem number 1, start with this chart, okay? So in this situation, you know the mass, you can always find that force parallel. Then, because of the fact that you know the coefficient of friction, you know that mu times force normal equals force friction. So that's mu times Fg cosine theta, okay? Which is going to be, if you want to do it all at once, that would be mu mg cosine. If you really, we can rearrange it a little bit and go mug cosine theta equals force friction. Okay? So again, your applied force going up is balancing out your force parallel, so you got to pay off the gravity mafia, and your force friction, which is also acting down. So if all goes well, your answer to number 1 is something around the legal drinking age. Okay? Not what it is when you think mom and dad are out of town. Okay? Not that any Mays High School student would do anything
That's
like that.
myself, but
Oh, Mays South. Okay.
yeah.
Whatever.
Sorry.
Yeah. All right. So, yeah. Like you guys are perfect angels.
Mhm.
Get over it. This is not my first rodeo, Sparky, okay? So, all right. So let's talk about numbers 2 and 3. And I'll show you this in just a second. So I want to hang this mass on the end so that this thing gets drug up at a constant velocity. Okay? So here's the deal. The only difference between the first problem and the second problem, the process is the exact same. The only thing that's going to happen is that when you get to the end, once you find that applied force, you have to divide it by 9.8 meters per second squared to get the mass. Okay? And the only difference on number 3 is that it's going down, so the frictional force is acting up. So if all goes well on number 2, the answer to number 2 should be around 0.4 kilograms. Okay? And your answer to number 3 should be around 0.2 kilograms. Okay, now that's a huge ish, okay? But it's going to be something close to that. So your answer to number 1 on those 3 problems is around 21. The answer to number 2 is around 0.4 kilograms. The answer to number 3 is around 0.2 kilograms. Okay? Now, notice on these, I've given you 3 significant digits on every value. Okay? Your answers should have 3 significant digits. Okay? Everybody cool with that one? Anything you want me to go over at all with that lab? Studio audience, do we have anybody zoomed in?
Reading
Okay, hi Reed Nate, good morning, good on you. Okay, thanks for joining us this morning. I feel like a radio talker, a TV talk show host. Like I should have
I
like
feel like
a
you
couch.
could just like keep going if you want to. Like,
Close. Anyway, what?
I feel like if you actually were like a talk show host, you could just like talk about random stuff for like hours.
Oh, yeah. Yeah. Well, you throw your topic. Oh, you said I look like, oh, well, it's close to Halloween. You said, here's a funny story about that. Speaking of random stories. So I was looking at getting new glasses. And, so I was at Sam's Club and it was, some college student. And she was helping me. I said, well, here's what I'm looking for and all this. Didn't know me from Adam, okay? So I try on a pair of glasses. It was actually the ones I have now. So for visual stuff. So I put these on. And I said, what do you think? She goes, she got a pause. She goes, kind of makes you look like a science teacher. And I said, well, that's funny because I teach physics and chemistry. She goes, oh my God, I am so sorry. It's like, it's okay, sweetheart. It's okay that I look like a science teacher.
She made it
That's kinda
physically
what I
like.
do. Yeah. And then one time I was flying out to go to a science conference. And I was just waiting in line at the airport. And these were other teachers from the Mays district, and they were also flying to the same conference. And I didn't know them from Adam, okay? And so they come up and go, are you a science teacher from the high school? And I was like, yeah, how'd you know? She goes, well, you just look like one. I think we're going to the same conference. It was like, oh my God.
Was she nice?
Well, and then you have my name. Okay, this is what I tell people. Look at my full name is Stanley Eugene Burkham. It's like, as soon as my parents bestowed that name on me, I was destined to teach physics. It's like, I could not be a professional quarterback with that name. Okay? Not going to happen. I was destined to teach physics based upon that name by itself. Okay. So, let's talk about the magnetic one. And I promise you, there's going to be a question. We're going to do some other stuff with this. There's going to be a question on that magnetic incline problem. So, here's the deal. So, you were at an angle of 2.1 degrees, not 21. Very shallow, okay? So, the first thing that they did is they let it roll without the magnet in it. And so, the only force to make that thing move is the force parallel. So that force parallel should be something around negative 0.3 newtons, okay? Because I'm telling you this is how I want this system defined. You got the weight of the cart, it's a 2.1 degree angle. That force parallel is going to be something around negative 0.3 newtons. So, and here's the trick. So, on number 4, I say determine the force acting to cause the cart to accelerate down. That's your force parallel. That's about negative 0.3 newtons. Then I say, if it's frictionless, guess what? That's also the net force, okay? If it's a frictionless system. So your answer to 4 and 5 are the same value, okay? Now, if there was friction, my net force wouldn't be negative 0.3. It would be less than that because there would be a frictional force acting against it, okay? So that's why those two answers are the same. Then you're going to find the theoretical acceleration, take the net force divided by the mass, that theoretical acceleration, again, it just randomly works out this way. Your theoretical acceleration on number 6 should be around negative 0.3 meters per second squared. Okay? It just happened to work out that way. Okay? So, all of your answers on 4 through 6 on that lab are something around negative 0.3. Okay? All those are going to be something around negative. They're different things, but they're all going to be around negative 0.3. Okay. So then you're going to calculate the experimental acceleration on number 8. So you're going to use distance equals 1/2 at squared plus v naught time. We released it from rest, so the v naught part of it drops out. You know how far it travels, which is 0.4 meters, because that's the length of the plates. So you're going to go 2d over t squared equals acceleration. You're going to have a negative displacement because it's rolling downhill. So your answer to number 8, oddly enough, should be something around negative 0.3. Okay? I'd like to say I had it planned this way, but it just randomly did. Okay? Now, on the back side, now we're going to try and figure out the value of this impeding force. Okay? So, you have the times, right? Now notice that the times are longer. So here, when you get into a situation like this, you want to focus on what you're holding constant and what you're changing. So when you still had the exact same inclined plane. You have the exact same force parallel. Okay, that force parallel is the exact same, whether that magnet is there or not. That force parallel is still there. Okay, nothing has changed. But what that magnet is doing, that magnet is providing an opposing force. So this is like the magnet mafia, okay? So the magnet mafia is impeding the motion of this thing as it's going down. So the magnet mafia is kind of like a second cousin to the frictional mafia, because it's always going to impede the motion of this cart. The magnet mafia or the friction mafia, either one of them is ever going to make something go faster. It's always going to work to slow it down. Okay, so remember this, because there's like, even when we get back here and on the test, you're going to have a question that's going to involve a magnet and in between these plates. So listen to me. The magnet mafia, just like the friction mafia, always makes you go slower. It never makes you go faster. Okay? Never. It always makes you slow down. You don't have to worry about hitting the brakes and then speeding up through the intersection. Okay? It'd be really weird if it did. Okay?
That black ice gets you.
Huh?
That black ice gets you sometimes.
Yeah, it's not going to speed up. They're just not going to slow down. Okay. So then you're going to calculate the acceleration based upon the data that you have for times. So on number 5, you're going to use this equation again. 2 times negative 0.4 divided by time squared. So your answer to number 5, that with the acceleration, I'm going to break the trend, okay? That acceleration is going to be something around negative 0.2 meters per second squared. Okay, so if you do that calculation right, you're going to get, this is on the back side, on number 5, you're going to get something around negative 0.2 meters per second squared. Okay? So here's the deal. You have the same force parallel acting down. Okay? That's still trying to force this thing down. So clearly something has to be acting upward that opposes that motion. So on number 6, you're going to calculate the net force using the acceleration just found. So you're going to take that mass that you have over on the front page, which is going to be something around 0.9. You're going to multiply it by that acceleration that you just found on number 5, and that net force should also be something around negative 0.2 newtons. Okay? So here's the deal. Think this through. You have a force parallel acting down that's about negative 0.3 newtons. Okay? Your net force acting down is about negative 0.2 newtons. Okay? So think this through. You know you walked into the room with 30 cents. Okay? You walked into the room with 30 cents. You check your pockets a little bit later, you're down to 20 cents. How much did you lose? 10. So that upward force from the magnet, right, is going to be about 0.1 newtons. because that's the force that's acting up the hill. And again, so that's going to be something around 0.1, okay? So here's what you know about the force of the magnet. You know it has to be pointing up the hill because it's slowing it down. So therefore, you know it has to be a positive number, and you know it can't be bigger than negative 0.3. Because if it was bigger than negative 0.3, guess what? The thing wouldn't move. So this is where you want to think through a problem before you even start it and go, okay, well, it's got to be an opposing force, because if it was in the direction of motion, my net force would be bigger, and it would be like negative 0.4, and the magnet would be making it speed up. Okay? So now here's how you can check that you got this right. Take the force on your magnet, add that to your force parallel, see if you get a net force of something around negative 0.2. Divide that by the mass, see if you get your acceleration. If you do, you did it right. If you don't, it was a train wreck. Okay? So on that drawing, on number 8, okay, here's what that thing should look like. You're going to draw a very shallow angle of 2.1 degrees, okay, not 30, not some random thing that you think looks good, okay. That's going to be 2.1 degrees. You can just put a box, or if you want to, you can just put a dot, I don't care. And then you're going to have 4 forces. You're going to have gravity acting straight down. You're going to have the normal force, which is going to be at a right angle to this surface. Okay, so that's not going to deviate very much because it's a pretty shallow angle. And then you're going to have your force parallel, and then the force from the magnet. Okay? And these two, this scale for these, because these are going to be really, really small, don't let 1 centimeter equal a newton, or otherwise you're going to draw vectors that are like 0.3 centimeters long. Okay? I'd at least let these be like maybe 3 or 4 centimeters equals a newton. Okay? At least. This one, if you've got the room and you just want to let 1 centimeter equal a newton, hey, that's cool. Okay? If you just want to do that. But because everybody's number is going to be a little bit different, in this situation, if you could write down the numbers, that would make it easier for me to grade. So when I go to look at them, instead of just, in addition to labeling them, also put down the numbers that go with them. And it's certainly, for the love of all things, make sure you indicate what the scale is. Okay, so you would say, oh, okay, you know, in the FG force normal, whatever scale that you're using that, for the force parallel and the force magnet, whatever scale that is. So you should have, I should clearly be able to see 2 distinct scales, okay? What you're using for the big ones and what you're using for those smaller ones, okay? Anything else? Are we good? Fantastic, you got it, great. Okay. All right, so let's pack up and go to the back. That was a big sigh, Sproles.
I'm sorry. You want me to sigh?
No, it's not a bad thing. I'm just saying it's a big sigh. Works, can you handle that?
Yeah.
Okay. All right, let's go. You're going to start with the simplest and go more complex, or start with the more complex and end up at the simple?
More complex, go simple.
More complex, go simple. Okay,
Yes.
Sproles is spoken. Okay.
Yeah.
I love it like I have one of them tech crew fellows here. Okay, so here's the deal. Now I'm going to explain what's going to be common to all 3 of these systems. All 3 of these systems have a 20-gram mass tied to the end of the string. Okay, so I've got this one with a 20-gram mass. This one, I've got a 20-gram mass. this one has a 20 gram mass, okay? So that's going to be the common theme, okay? They're all going to involve a 20 gram mass hanging from the end of the string. Now, let's start at the beginning. If let's say I gave you something simple. I said, hey, here's a 20 gram mass. What does the 20 gram mass weigh? So Ismail, what's the first thing you're going to have to do with the 20 grams? Convert it into, by dividing by 1,000. There's going to be 0.02. Multiply that by 9.8, you get 0.196 newtons. Okay? So let's just round it up to 0.2. Okay? So here's what's going to be a common. I got a downward force of 0.2 newtons on this. Okay? 0.2. Technically it's 0.196, but let's just call it 0.2 because that's easier to say. Okay. Now, so here's the deal. So I have a 0.2 Newton force pulling down here, and that's pulling on the string. So why isn't this thing accelerating? My God, I've got a 0.2 Newton force acting on it. Why doesn't it accelerate?
Because the cart weighs more.
That's potentially, the cart weighs more, but I've also got this thing sitting here, right, blocking it from maybe rolling down. But no matter what, the sum of all of these forces is going to add up to equal to 0. So what's happening is that whatever is what's happening with this 0.2 newtons isn't enough to make this thing accelerate to overcome whatever forces are acting in the opposite direction. So right now everything is in equilibrium. Okay? I got a 0.2 Newton force. That thing isn't accelerating. I got a 0.2 Newton force pulling down on that. That's not accelerating. So right now, even though 0.2 newtons of force is acting on every system in all three of these, nothing is accelerating. So if I tell you, hey, I'm going to apply a 0.2 Newton force to an object, what's going to be the acceleration? The acceleration might be 0. It might not move. Okay? Now, I'm going to change this. I'm going to take this. I'm going to set this like this. So the first thing I'm going to do, I'm not going to have the magnet involved. Okay? So I'm going to go, I've just got this like this. I'm just going to let go of it. Okay? Now, let's assume for now that this is a frictionless track. So, just make this observation. I let go of it. What does it begin to do?
Accelerate.
Accelerate. So which forces, so what forces are involved when I let go of this? Okay? What forces are involved in this motion?
Force parallel.
Okay, so the force parallel, which is going to act which way?
Downhill.
Down. So this is acting down the hill. So I have a force parallel that's acting down the hill, right? Now, what's happening with the 0.2 newtons? Which direction is that force acting?
Applies as like up.
That's up the hill, right? Is there anything else in this direction of motion?
Not in the horizontal direction of motion.
Yeah, not along here, okay? I'm not accelerating this way either, which would be really weird, okay? So I have a normal force, right? Because I'm on an inclined plane. I have gravity pulling down on this, but I'm not accelerating in this direction. So the only thing I'm worrying about is what's happening here. So, start with this. I let go of it. Which force has to be bigger?
Force parallel.
Yeah, because that's the direction of the acceleration. So, if I let go of this and I see an acceleration, oh, this force going down has to be bigger than the 0.2 newtons that's being pulled this way. So, now we're going to change it. So, I want you to just get a visual, okay? See how fast that's accelerating like that, okay? Now, what if I disconnect this string and let go of it? Now what's going to happen to the acceleration?
It's going to go a lot faster.
Alexis, what's going to happen to the acceleration?
It's going to go faster
Why?
because there's no longer a force going in the opposite direction.
Beautiful. But what's still there?
The force parallel.
Yeah. So now when I let go of it, I get a much bigger acceleration. Okay? I put this on it. It dramatically slows it. Now I'm going to put the magnet in here. Okay? So now when I do this, hold on, we're actually rubbing. Okay? Now when I do this, Notice that that acceleration is even less. So here's the question. When I let go of this, what's the direction of the force from the magnet? So which direction is the magnet mafia acting?
Down.
Up or down?
Down.
Who said up? Why is it up?
Because
Just based upon an observation, how do you know that that force from the magnet is acting up?
because it's slowing down, so the force applied has to be smaller.
Fantastic, okay? So when I let go of this, now, is my net force still acting downward? My net force is still acting down, right? So when I let go of that, I still know I still have an overall negative net force. But now I have two things that are working against it. I have the magnet mafia, which is opposing that motion, and I also have the gravity mafia, which is opposing that motion. So I have two things that are acting up the hill, and only one force that's acting down the hill. Now, is my overall net force still down the hill? Yeah, okay. Now, let's say that we could do this, and we could say, okay, hey, here's our initial velocity, that's 0. I can measure the acceleration, right? One of the things you're going to have to do on the test, you mark my words, you're going to have a problem like this. It's going to involve a cart like this, a magnet, and a weight on the end. Okay, you mark my words. This problem is going to be on the test. Okay, in case you haven't noticed, I write the test. When I tell you a problem is going to be on the test, I'm not lying. Trust me. So it's like, oh, I'm going to tell them that's going to be on the test, and I'm not going to put it on there. Ooh, okay.
I'll get them there.
I'll get them there. Oh, good one. I outsmarted some teenagers. Woo. Okay. So when I tell you it's going to be on the test, it's going to be on the test. Now, the last thing you're going to have to do, or one of the things you're going to have to do on this problem, is you're going to have to find the acceleration of the system. You're going to have to find the first. I'm going to tell you exactly how this problem is going to play out. You're going to find three things. The first thing you're going to find is the net force. The second thing you're going to find is the acceleration. And the third thing you're going to figure out is how long it's going to take for this thing to travel. Okay, those are the three things. So your net force, you're going to have like a weight, you're going to have this, you're going to have force parallel. Okay, you're going to find the overall net force. Then I'm going to ask you to find the acceleration. Now, this is what you're going to see common to all three of these situations. When you find the acceleration, okay, you're going to know the net force. So you know net force equals mass times acceleration. To get the acceleration, you're going to take your net force and divide it by the mass. But here's the question. Which mass do I use? Do I use the mass of the cart? Do I use the 20-gram mass on the end? Or do I use all three of them? Or do I use the sum of all of them?
Some.
The sum. So, listen to me. On this problem, okay, you're going to find the acceleration. Your last step, and this is what's going to happen on all three of these, you always divide by the total mass of the system. Okay? That's the common theme. You always divide by the total mass of the system. Okay? So it would be this plus the 20 grams. Now, here's ironically where this problem goes south, is that you all screw up the conversion from grams to kilograms, like you divide by 100 or something and you get like 0.2. On this problem, make sure, and I'll tell you, it's going to be like 20, 30, 40 gram mass. It's not going to be very big, okay? Divide by 1,000. Don't divide by 100. Don't shortcut that process. Literally, that's the most common mistake that's made on this problem, is converting grams into kilograms. Okay, so you got that one. Now, if I take off the 20, and let's say that I put a 50 gram mass on here, okay? Now if I put a 50 gram mass on there, now listen to me very carefully when I ask you this question. By putting a 50 gram mass on the end, what has that done to the force parallel?
Nothing.
Absolutely nothing. It's still the exact same card, it's still the exact same angle. My force parallel is still the exact same. But now the cart's going this way. So now which direction is the magnet mafia acting?
It's still acting back.
It's still in the opposite direction of motion. The magnet mafia always acts in, so if it's going this way, the magnet mafia is acting this way. If it's going this way, the magnet mafia is acting that way. But now, what do you know about the applied force from the 50 grams? That has to be
Bigger.
bigger than these two forces acting down the hill. Okay? So this is when you just make an observation and go, okay, hey, I'm going to let go of this. All right, cool. Whatever this force is has to be bigger than the forces going down the hill. Good with that? Okay. All right. So let's move to this one. So I got this cute little 20 gram mass, right? Okay? 0.2 newtons. I'm going to take this out. I have a 1 kilogram mass, and this card has mass of 0.5 kilograms. So now when I let go of it, okay, oddly enough, it begins to accelerate. So why is this system so much simpler than that one?
There's no incline or force parallel.
Yeah, I got, all this is boom, I let go of it. Well, hold on, that fell off. It's like, why isn't it moving? God, did I break gravity?
We just broke it.
I broke physics. God, there goes my teacher of the year nomination. Okay, what happened? Well, I was good till I broke physics. Okay, so now when I let go of it, wow, it begins to accelerate. So if this was a frictionless system, what's the only force available to make this thing move?
The force applied.
Created by this thing, which would be 0.2 newtons. So, again, the only thing that can make this move is 0.2 newtons, right? So, I got a 0.2 newton force acting on a 1 kilogram mass, a half a kilogram mass, but when you find your acceleration, you also have to add in this, because this thing is being accelerated too. So this is why this system is so much more simpler. I don't have force parallel. I don't have the magnet. I've got a 0.2 newton force accelerating 1.5 kilograms, easy peasy. Now, but what if there was friction? If there was friction, what would happen to the acceleration?
It becomes slower.
Or it'd be less incline.
Yeah, because there would be an opposing force. I promise you, it's going to be the last problem on the test. Mark my words, okay? Or the second to last, I don't remember. It's going to be towards the end of the test. I'm going to have a situation like this, and you're going to have two different types of problems to work. One where you let go of it, and there's no friction, and the other one, you let go of it, and there is friction. That's going to be the last problem or the second to last problem on the test. Mark my words. It's rolls.
Are you going to give us the force friction, or are you going to give us like mu? Or
I'm going to give you mu. I'm not that nice.
Dang.
But let's talk about that. I'm going to give you mu, and you're going to have the mass of this. When you calculate the force friction, only worry about this mass, because the friction is only going to occur right here. Actually, Maddie, there's like a smaller block of 2x4 over there. That one, beautiful. Thank you, dear. So,
So worry about the mass of the cart and the 1 kilogram, or just the cart?
is there one that has like a hook in it? What do you mean?
So the mass of the cart plus the 1 kilogram?
Yeah, because
Okay.
it would have. I'm just going to give it to you as one value of mass.
Okay.
What is this? Okay, all right, what enough. Ah, stupid friction. Okay,
Oh. It's breaking physics again.
that'll make it move. Okay, there we go. All right, now there's clearly friction with this block, right? So if I gave you this problem, so here's a 100 gram mass. 100 grams is how many kilograms? Mental math. 1 or 0.1?
0.1.
0.1. For God's sakes, this isn't 1 kilogram. Okay? So this is 0.1. More mental math. 0.1 times 9.8 meters per second squared gets you. So help me God. If you, if
0.98.
Huh?
0.98.
0.98. I've always said we should before we give you a diploma, we should be able to ask you like a simple math question before you walk across the stage. Like if I ask you,
2 plus
what's
2?
0.1 times 9.8, and you can't do that in your head, you don't get the
In our
diploma.
defense here, though, graduation's not at 8:30 in the morning either. Like, it's early. My brain's not awake yet.
Oh, get over it, okay. Hopefully you're not a surgeon that does wing operations. Oh, sorry, your son's paralyzed, I just wasn't quite awake yet.
My
Had
bad.
I done that at 3 o'clock in the afternoon, your son would have been fine, okay? He's
God.
paralyzed now, but it's okay. Okay, so I got a 0.98 Newton force acting down this way, right? So friction only occurs here. So when you calculate the force friction, only use this. This has nothing to do with the friction that occurs. It's only this. I could tie an elephant on the end of this. It's still going to be the exact same amount of friction that's going to happen here. Now, I put the 1 kilogram mass on there. What have I done to my applied force?
Nothing.
Nothing. I have a 0.98 Newton force acting this way, right? Guess what? The frictional force is so much that
It's not moving.
it's not moving, okay? So again, I'm applying a force. What's my acceleration?
0.
0. Okay. So here's the third type of problem that you're going to have. Mark my words. This is going to be the third type of problem. So here I have a 20 gram mass. So here's the continuing theme. I have a 20 gram mass. Now, that 20 gram mass pulled that whole cart up the hill. That 20 gram mass drug that cart, right? But now I've got a 20 gram mass here and I got a 50 gram mass over here, right? Now when I let go of it, what's going to happen?
The 50 gram mass is going to go down.
Yeah. The 20 gram mass here, right, is going to go up. So how can a 20 gram mass here drag a cart with 1 kilogram mass on it, but a 20 gram mass here, same thing, same 0.2 Newton force going down, but it goes flying up.
Because the 0.5 kilogram, or 0.5, yeah. 0.05 has more applied force than the 0.2.
Yeah, exactly. So in this
I just had a
situation with
seizure.
an outward machine, this is still pulling down at 0.2 newtons, okay? This is about 0.5 newtons, okay? Because it's a 50 gram mass. So this is 0.5 newtons, this is 0.2. So in this situation, and again, go back and revisit your labs, we're calling this the applied force. This is now the opposing force. So on the first two machines, the 0.2 newtons was the applied force because that's what was making it move. In this situation, the applied force is going to be the 0.5 newtons, and this is going to be the opposing force. But again, what's the common theme? When you go to calculate the acceleration of this system, you're going to calculate your net force. So let's say this is 0.5. Let's say this is 0.2. So what's my net force? If this is 0.5 and this is 0.2.
Like, they're both newtons, right?
Yes, this is in newtons.
0.3.
This is 0.5 newtons. That's 0.2 newtons.
Would it be negative 0.2?
Or it's just going to be 0.3. If you want to make it positive, negative, I don't care what we're going to do. Okay? But it's going to be 0.3. So my net force is 0.3 newtons. To get my acceleration, do I divide by the 20 grams, the 50 grams, or 70 grams?
70.
70 grams. Divide by 0.07. So here's what's going to be common to all three of these. At the end of the day, you're going to calculate an acceleration. No matter how you distribute that mass, you always divide by the total mass of the system to get that acceleration. Okay? Got it? Good? All right, back we go. Right. Okay, so as you prepare for the test, I've got a review. Just as always, you're going to have a blank set of problems. You're going to have the answer keys to them. You know that I'm going to give you a rocket problem. I'm going to give you some force applied, and I'm going to ask you to find the acceleration of the rocket. Okay? You know that's gonna be on there. You know you're gonna have an inclined plane problem on there, okay? You know you're gonna have to know the 4 fundamental forces. Now, the questions about the 4 fundamental forces is gonna be on the multiple choice portion of the test, okay? You have 4 fundamental forces: gravity, electromagnetic, strong nuclear, weak nuclear. The weak nuclear force, I'm going to have it there, don't choose it. I'm just seeing if you all pay attention. Do not choose the weak nuclear force. It's not going to be one of the answers. I promise you it's not, okay? Because that only involves radioactive decay. It's important, we wouldn't be here without it, but that's not going to be one of the answers. Gravity, that's pretty straightforward. Electromagnetic, okay? That's the most diverse. That's what creates friction. That's what allows me to write on this pad. That's what allows you to see it. It's what allows us to have electricity. It's what holds our molecules together. It's what keeps this 1 kilogram mass from falling to the center of the earth. Because without the electromagnetic repulsion of the bits of matter that make up this and the table, that would just sink through to the center of the earth. Okay? So, gravity is pretty straightforward. The strong nuclear, and I swear to God, I'm going to ask you this question. I'm going to ask you, what is the strongest force? What are you going to pick? Strong nuclear. So help me, if you miss this, I'm going to flunk you on this test. Okay? And I'm going to tell you that on the test. Okay? If you miss this question, I will flunk you. That's just going to be a statement on the test. Mark my words. No pressure.
Nice
But,
knowing you guys.
Just don't miss it.
huh? Just don't miss it. I have it on video that I told you what the question was going to be. Okay?
And the answer.
And the answer. Not only did I tell you the question, I told you the answer. It's a gift. Accept it, okay? Now, what's the only situation where you wouldn't have to pay off the gravity mafia?
In deep space.
Yeah, and unless I tell you, and if I tell you, hey, you're in deep space and you don't have to worry about gravity, then your applied force is your net force, okay? But unless I tell you that, you have to pay off the gravity mafia. Okay, I'm done. So, I'm going to give out the review. I'm going to give out the answer keys to it. You've got, all of your assignments. I'm going to email you back those inclined planes assignments that you all sent in. I've got those graded. I'll email those back to you so you have those. And then give me those 2 labs. The sooner I can get those, I'll try and get those graded and back to you certainly by like Sunday afternoon so you have those to look at for the test. Okay? So I'm done. Let's call it a day and we'll go from there.